I'm Lila Cheek, and this is the Physics 2 Lab 3. So the purpose of the lab was to examine circuits that contained resistors in series and in parallel, batteries, and capacitors. It's done using the PHYS simulation. This allowed the experiment to be purely theoretical, so we don't have to deal with real world phenomena such as wire or battery resistance. Values of conventional current and potential difference were found using a ammeter and a voltmeter. And then the behavior of the resistors and capacitors was examined. Some fundamental principles that we need to know for this law is Ohm's law, which is that delta V equals IR, the loop rule, which is that if you add all the delta V's for all the loops together, it should be 0. We also need to know energy and charge conversion, which is that the total electric charge must be conserved in the circuit, and that resistors in series have equal resistance. So the first thing we did was the prediction of the energy and charge conversion. So we have this set up here. We have two batteries that are each 1.5 volts, and then we have a 47 ohm resistor and a 100 ohm resistor. So the equation that we can set up from the loop rule is that 3, which is 1.5 from each battery, is equal to 47I plus 100I, which shows that I1 is equal to I2, which is 2.4 milliamperes. So then we tested this in the PHYS simulation. We found that our predictions were correct. As you can see, both currents is 0.02 amps. So what if one of the ammeters was backwards? I tried this, I don't have a picture of it, but nothing would change. Both values are still 0.02 amps. What if one ammeter was replaced with a voltmeter? That's on the next slide. The voltmeter now reads 3, while the ammeter is now at 0. So the change in volts is 3 across the gap, so it becomes 3 over here because of the two batteries, and then over here it's 0 because there's no current flowing through it, so the difference in that is 3 volts. That's why it says that. So the voltage change across each component, from A to B, it's 3, and then from B to C, it's 0, from C to D, it's 0.96, from D to E, it's 0, from E to F, it's 2.4. Those are passed to the two resistors, and this is between the batteries. And then for the rest of it, it's 0. So as you can see, -3 plus 0.96 plus 0.2 or plus 2.04 is 0. So that shows that it follows the loop rule. This is the graph of the volt changes. This just basically demonstrates that delta V is 0. Again, could because you start down at 0 and then you end up back at 0. So once again, just demonstrates the loop rule. So changing the circuit, the ammeter was added to be parallel with the 100 ohm resistor that's right here. This changes the current to 0.06 amps, as you can see. This is because the current that used to flow through this resistor now flows through the ammeter instead. So it effectively lowers the total resistance from 147 ohms to 47 ohms, which then makes the equation 3 minus 47I equals 0. So I equals 0.06 amps, which is what's shown here. The resistance in each element of the circuit can be calculated using delta V equals IR, which you can rearrange to R equals delta V over I. So for the first resistor, that's 0.96 divided by 0.02, which is 48, which is around 47, which is what it actually is in the simulation. And then for the second one, we have 2.04 divided by 0.02, which is 102, which is again around what it is in the simulation. And then for the rest of it, it's 0. These values come off that table that I showed a few slides ago. Then the RC circuit, we have a 9-volt battery, a light bulb, which is our resistor, and a capacitor. When we have a 10 ohm resistor, it takes 15.5 seconds to charge the capacitor and 15.4 to discharge it, which you can see are very close. And then there's also the 20 ohm resistor, which takes 27.6 seconds to charge and 27.6 seconds to discharge. So that's also very similar, but as you can see, the 20 ohm resistor one takes a lot longer to charge and discharge than the one with less resistance. So the time-dependent circuit data, basically we did this with the 20 ohm resistor, and then we paused it every couple of seconds to note change in time and seconds and the voltage reading. So this is the voltage reading, this is the time, and then this shows the natural log of V divided by V naught, which is VO is just 9. And then this is a graph of the data. The slope is equal to 1 over RC value. So that shows that RC for this data was around 1.44. So what if? First what if question is, what if you were doing this experiment in real life and used an actual ammeter rather than the ideal simulated ammeter? Real ammeters have resistance, so the ones in the simulation do not. So this would affect the current reading in the simulation, where the ammeter is placed next to the resistor, because some of the in the simulation, all of it flowed through the ammeter because there was no resistance. But because they both have resistance, in this situation, some would have gone through the ammeter and some would have gone through the resistor, so it would have changed the reading. And the second one, what if you were doing this experiment in real life and used a real battery to charge a real capacitor with no resistor in the circuit? If we had done this in our model, the capacitor would have charged instantly because there would have been no resistance at all because there's no resistor. But if we did it in real life, it wouldn't charge instantly because the battery itself would have some resistance. But it would still be very quick, but just not completely instant like it would be in a model.